All right. So this is our first chapter, matter and energy and atomic perspective. Most of you have had some of this stuff in high school. There's a bit of a delay from here to there, but these are our learning goals. We've got to master the basic terminology. Terminology is key in chemistry. It's kind of like what I was just saying. Because when you think about it, the one question on the quiz that had poor performance was the one that said a molecule. And then there was multiple choice underneath it, right? A molecule, the correct answer is a molecule can be an element or a compound. That is the correct answer. The one that a lot of people put that was wrong, a molecule must contain at least two types of atoms. Wrong. H2. Right? Is a molecule. And it's an element. Okay? So it doesn't have to contain at least two types of atoms. This is where it gets a little confusing because we say that an element is a substance that can't be broken down to simpler things. Well, wait a second, can I break that down? Well, when you think about the periodic table and the elements, you're thinking about hydrogen because the periodic table is built on atomic numbers, numbers of protons, right? That is how it's structured. That is the identity of an atom. If I tell you it has one proton, that means it is hydrogen, no exceptions. And if I say it's hydrogen, that means it has one proton, no exceptions. That is the way the periodic table is built. Bless you. It can change the number of electrons, and numbers of neutrons can change within hydrogen, and it's still hydrogen, but not the number of protons. So when you think about the periodic table, you're thinking about the element hydrogen. They're hydrogen atoms that all contain one proton. It's just that hydrogen, if you put a bunch of it together, is immediately going to form hydrogen gas. So in its elemental state, it exists as hydrogen gas. Okay? That's where it's a little confusing because you could say, well, I could break the hydrogen gas down into single hydrogen atoms. That's not really what we're talking about because the element itself is the hydrogen atom. And that you can't break down to simpler elements by chemical means. You do it by physical means. High energy physics means, now I say physical, I don't mean physical as in like filtration. I can separate hydrogen right into protons, electrons, and neutrons. But you need high speed accelerators or you need high energy atmospheric chemistry, like in a star or something like that, to separate those out. Okay, so the terminology is key. And then we're going to look at the scientific method, basic structure of matter, COAST. If you like this, use it. If you don't, ignore it. But dimensional analysis, I don't know how many juniors and seniors or sophomores have come to me and said, hey, Dr. D, I'm so glad you stressed dimensional analysis. It really does make your life easier. I don't know how many times I've sat and stared at a problem and said, I have no idea where the heck to start. And then I look at the units and say, oh, wait, I need my answer in grams. I've got this, I divide by this, boom, I get to my answer. It doesn't always make logical sense to say, why am I multiplying this by this and dividing by this? It doesn't always make clear logical sense that way. So the units will actually lead you through. Okay, so these are some of the terminology and definitions you need to be familiar with. We're not going to talk about this at all. Because it's stuff you can get from your reading. You've been quizzed on some of this a little bit already. We just talked about, molecules. I like to think of atoms as kind of what makes up the elements, and molecules with a caveat make up the compounds. And the reason I say with a caveat is because not all compounds are composed of molecules, right? Your ionic compounds. So you're reading sodium chloride, things like this. There's no such thing as a sodium chloride molecule. Doesn't exist. Okay? It's a crystal. Okay, we'll get into that a little bit. So you can't say that actually, that molecules make up. You say molecules or, ionic formula units make up compounds. What's the fourth state of matter? Plasma, which is not listed there because it's kind of an, not one of the three basic ones. Where do you see plasmas? Besides really old TVs, you still have one. Stars, right? Our sun, right? That's our plasma in the sky. So you'd see high energy situations in which these fluorescent lights, okay, can have these charged particles because it's like a plasma. Plasma TVs are based on this concept. Any questions about any of the terms on this slide? So here he goes with breakdowns. It's a classic figure that's in every chemistry book I've ever looked at. All of matter can be separated by physical processes. What do we mean when I say physical versus chemical? Okay, not changing it, right? Still carbon dioxide. It goes through a physical process. It's still carbon dioxide. You think about, and you can apply this to not only processes like, but also, not only characteristics, but also changes, physical changes or physical properties, chemical changes, chemical properties. So someone give me an example of a chemical property of a substance. One, what's your first name again? Andrew says boiling point. Agree or disagree? You're shaking your head no. That's physical. That's right. It's physical. Why? Well, if I take water and boil it, it's still water. And that's the way I say water, by the way. It's spelled W-A-D-D-E-R. That's the northern accent. Sorry. I can't even say it the southern way. It's a what? I can't say it. Watch it. Anyway, it's still water, right? I boil it, it's H2O. What you'll learn in chapter 6, which we saved till Gen Chem 2, is what you're doing is separating the individual water molecules from each other. They're attached to each other. And so you're going to go from liquid water to gaseous water where the molecules are much more free, but it's still H2O. So what's a chemical? Give me an example of a chemical. Then I asked for chemical and I got a physical. Yes. Iron rusting. Very good. So we got iron rusting. It's no longer iron. It's iron oxide. Okay. And there's different forms of rust. You know, iron is used to make steel and has strength and durability. We use it to make steel. And the rust is useless, right? It just flakes away. No one wants the rust. We spend billions of dollars a year replacing the rusted metal in this country. So that's a change in the compound, right? So those are examples. So as you move down here, you've got elements and compounds. You can see those are both considered pure substances. This is a pure substance. Just because you say, oh, hydrogen's mixed with oxygen. No, that's not the way it's used in definition wise of chemistry. We're talking about physical, okay? You can't break the hydrogen from the oxygen by physical means. If we did, we'd have a pretty cheap, endless supply of hydrogen gas and we'd rid ourselves of fossil fuels pretty darn quickly. But no, we got to expend energy. And if we can do that, and separate out the hydrogen, we can wean ourselves from fossil fuels, which has to happen now, not later. Okay? When I started teaching here, I used to tell my students, in your lifetime, you won't have to worry about the consequences of climate change. I no longer say that. Okay? I'm worried for my kids' future and my kids. They don't have kids yet. I'm not a grandfather just yet. They're like your age, my kids. I'm worried about their kids also. So people are talking about getting this hydrogen, but they're talking about doing it in ways that take too much energy and they're using non-renewable energy to get it. What we need to do is use solar power to split the hydrogen from the water. Then you have a truly renewable source and a source of hydrogen that we can use to power things without using other means that require energy that comes from dirty fuels. So it's still a pure substance, water, carbon dioxide, right? We're talking about a physical process. If I mix salt with water, that is no longer, right, a pure substance. We're now over here as a homogeneous mixture with salt mixed with water. And heterogeneous would be something that separates out, like salad dressing, oil and water don't mix, that. Questions? Scientific method. I'll let you read on most of this. There's one important point I want to make. Is first of all, there's no set order in which things happen. Yes, there is a general idea of how things happen. Usually you make an observation first, right? I mean, that's obvious somewhat. And there is a general sequence that we show in books, and I think I have it right here. But you do things over and back and forth. Now, there's two things I want to share with you. One is very pertinent today, and that is why a lot of people aren't getting the vaccine. There's not that many anti-vaxxers, okay? The numbers show that a lot of people aren't getting vaccinated or because of their concerns about this vaccine, okay? And the reason is this. People's confidence in science has been shaken, not because the science is questionable. It's because you're seeing the scientific method, the scientific process unfold on the news in front of your very eyes at breakneck speed, which has never happened before. Usually the stuff that you're seeing right now happens in small conferences with just scientists where there are no journalists allowed and no public allowed, okay? Conferences that I go to present my paper, okay? And other scientists rip it apart and say, wait, you didn't do this. Or wait, I have a question. Why didn't you look at this? Or we go back to the lab and we get more data and say, they were right. Now it's better and we have this. We go to another conference, then we publish the paper. You're seeing that happen. So you think it's, scientists know what they're talking about. First we wear a mask, then we don't wear a mask. No, it's because we immediately told you that the data shows that it's maybe spreading on the surfaces. And then no, it's actually an aerosol. Why? We got more data. That's what you're seeing. You're just seeing the scientific process. That's the beauty of science. That's the way it works. Okay? That's never happened before. And it's because it's a pandemic, and because it's this world health issue that you're seeing unfold in front of you. So we make observations, we make hypotheses, which is just an educated guess. We then test it, collect data, revisit the hypothesis, right? We test it more, we get more data, we go through this whole process. And then you come down to what laws and theories. And, you could think of a model as a law. Classic one is, I use physics here. I'm a lover of science, not just chemistry. That's a classic, if you will, law. Newton's law of motion, right? Second law of motion, F equals ma, force equals mass times acceleration. You can think of that as a model. It models data. It doesn't explain anything. You put the numbers in, you get a number, you realize, hey, if I increase the mass, then, well, let's say it like this. If I increase the force on a given mass, then the acceleration is going to increase. Okay, you can look at the relationship like that. It doesn't explain anything about friction or why the acceleration changes. It's just a model. Now, what's not on this list right here is a theory. So the question becomes, well, what's a theory then? Compared to a law, when's a theory come in? What is a theory? It explains it more in depth, definitely, right? Think of your classic theories. Evolutionary theory, Big Bang theory, atomic theory, right? These are broad, huge concepts, right? They might incorporate some laws in them, but they're going to have lots of explanations. If anyone tells you that a theory is fact, they're pulling your leg. A theory is meant to be moldable, to be reshaped. Okay. Typically, we don't throw out theories, we simply modify them as we get new data, new information. Occasionally, you have these revolutions come along. You look at quantum theory, which is chapter 3. We didn't throw out classical physics, right? We started to realize that atoms behave very differently than balls and planets do, right? Things on a very small level behave differently. We didn't throw out classical physics. We simply said, oh, wait, classical physics no longer applies to really small things, subatomic particles. And we developed this new theory. So we've simply just restructured classical physics and say, okay, it doesn't cover this anymore. We have this new theory that covers this. That's typically the way it happens. Now, some of the old theories back, hundreds and hundreds of years ago, things like, spontaneous generation, stuff like that. Well, of course, we threw those out once we learned stuff and realized that, bacteria just didn't spontaneously generate. Okay, they're there. So it makes sense really what a theory is. So it's a broad explanation. Might have multiple components to it, designed to explain things in more depth. Moldable, changeable. I'll let you read these. I already talked about the law of multiple proportions because I got that question on it. On page 5 in your book, they talk about this. But once again, like I said, I'm not going to say to you on an exam, the law of definite proportions is. Keep in mind, it's open book, open notes. And that's not an appropriate question for an exam anyway. You can just go like this, okay? So the exams are structured a little bit differently because they're open book, open note. Also, as with the quizzes, the exams are pooled questions, completely randomized, and everything's mixed up. So you all didn't see the same quiz. I mean, some people saw the same quiz because there's only so many choices, but it's a pool of questions. Okay. I think I asked a question, intensive, extensive on the quiz, didn't I? Yeah. So intensive are independent of the amount of substance. So the density of lead. It doesn't matter if I have a speck of lead or a big block of lead, the density is the same because it's mass per unit volume, right? So the speck has a smaller mass, but also has a smaller volume proportionally, so the density is the same. That's an intensive property. Extensive property depend on the amount of substance. So how much heat is going to be released when I burn this fuel? That would be an extensive property because the heat released will depend on how much fuel I have, right? And then we already talked about physical and chemical. Any questions on physical versus chemical, intensive versus extensive? These slides are all posted online. So if you don't get something down, you have it. A lot of people like to write. It's good. Actually, when I get students that come to me in my office and ask Dr. D, I'm struggling. What can you suggest? I always tell my students, write and vocally say it. So one thing I learned in college, I can't remember when it was, but I used to go to vacant classrooms late at night. I was one of these procrastinators and would cram all night as an undergraduate, not as a graduate student. When I got to graduate school, I got my head on straight. I took 3 years off and worked for a while. Fox Chase Cancer Center in Northeast Philadelphia doing cancer research. I figured out that if I went into a classroom and wrote and said the stuff, I remembered it so much better. So you can do that with a tablet. You can do it on a piece of paper with a pencil. But I would write stuff out. And as I wrote it and said it, and they've shown this through studies, psychology studies, the more input you have, vocally, visually, and writing it, you remember it better. And you think things through. So as a result, I talk to myself all the time now. Too many years of going like this. A molecule is, and that helps to remember stuff and helps to study. All right, practice distinguishing chemical and physical. Which of the following properties of copper and which are physical? We'll put a P next to the physical ones and a C next to the chemical ones. First one, physical or chemical? Physical, right? Second one, color is always physical. Third one, chemical. That's the rusting, right? Last one, physical. And I know melting boiling points are going to be physical because it's still copper. It's just liquid copper instead of solid copper. Okay. Density. So this is one way in which you can measure density. And I don't even know what's going on in lab anymore. There's been so many changes over the last couple of years. We used to do a density lab where you did some of this displacement. You guys still doing that? Did you do it yet? Did anybody do the lab yet? No. Just safety. So maybe next week you'll do it. But this is one way you can measure the volume of a substance that's got an odd shape, right? Yeah, if it's a cylinder, I can calculate the volume pretty accurately. But if it's a gold nugget, good luck, right? So you can do volume displacement. And the volume increase, you just subtract that volume from the initial volume, and you've got your volume. And then you weigh it on a scale, and you can determine your density. So that's pretty straightforward. That's something you should be prepared to do on like an exam question. I give you a volume, I give you a new volume, I give you a mass, you calculate the density. Maybe we'll do something like that on Monday, Tuesday. I keep saying Monday. So here's this COAST framework. Once again, if this works for you, go for it. It's in the book as something they've introduced a while back. It makes sense, and I do this somewhat just logically. You collect your information, you think about it, right? I always tell my upper division students, same thing, to think about your answer. Does it make sense? Do you have a question, Megan?
Can we just do dimensional analysis?
This is just a suggestion from the book. I don't do what works for you. Some students, this works and they like it. But I always tell my students to think about their answer. And I've had not graduate students, I won't go that far. I've had upper division students. I do a little calculation. I'll ask them to calculate, a mass of something. The one we've done is like a bacterial culture that's growing, and it only grows for like 48 hours. And based on the generation rate, what's the mass of that culture? And, they come up with numbers like, and this is a culture of bacteria that's been growing for 48 hours. It replicates and doubles itself every 48 hours. So, that number is so small, it's ridiculous. That's probably smaller than the weight of a single bacteria. Okay? Think about your answer. If I asked you to calculate the weight of the mass of Pluto and you come up with that number, the negative exponent tells you something's wrong, right? You probably just divided by something, then you should have multiplied or whatever. That's what I mean by think about the answer. It doesn't make sense. Okay. A metal coin taken into the laboratory found to have a mass of 3.90 grams. The diameter is 1.91 centimeters, and its thickness is 0.150 centimeters. What is its density? And I've given you the volume of a cylinder because I don't expect you to remember that. So basically, a coin is just like a really flat cylinder, right? Must be my three-dimensional coin there. Just a really flat cylinder. So we can use this volume of the cylinder, right? And of course, the radius is 1/2 the diameter. And we're given the diameter, and we've got the height, which is the thickness here, right? So we should be able to calculate the volume, no problem. Keeping an eye on our units, make sure what we're looking at here. We got centimeters and centimeters, so that's no problem there. You got to make sure your units are always in the same, right? Anytime you do a calculation like this. So there we go. We just plug it in. Pi, there's the radius. That's 1/2 of this. Divide this by 2. and you get 0.955. And then we got the height, which is the thickness. And notice my final units, centimeters cubed, right? Why? Well, this is centimeters and it's squared, and this is centimeters. So you do the same thing to the units that you do to the numbers, right? And that makes sense. A volume is length cubed. So your answer needs to be length cubed. That's the other thing too. Your units should make sense. And if you follow dimensional analysis, if you get the wrong units, it lets you know you did the problem wrong. If you're asked to calculate a mass and you wind up with, meters over grams, oops, I did something wrong, right? So the units kind of cue you in. As long as you carry them along with all your calculations, they'll cue you in. Hey, you made a mistake. Questions about this calculation? Good? Oh, we didn't finish it. Density, of course, we're asked for density. So we got to take the mass divided by the volume. You get 9.07 grams per cubic centimeter. These are those homogeneous and heterogeneous mixtures. I don't think I need to say much here unless anybody has a question. When we think about these things, we're thinking about the bulk property. It doesn't mean on an atomic level you can't have groups of atoms together, a bunch of vinegar here and a bunch of vinegar here and a bunch of oil here. It means on a macroscopic, level, maybe just looking at a microscope. Atomic level, you can always have heterogeneity. So that visual bulk property is going to be homogeneous. Or I shouldn't have said vinegar and oil because that's heterogeneous. And then, so if you have salt in water, you can actually have little groups of salt ions and things like that. Okay, so we can separate these physically. And, one way to do this is filter it. Another way is distillation, right? So I can have two substances. And if they have different boiling points, I can distill it, I can boil it, right? And keep it below the boiling point of one of the substances, and the other one boils off, right? And I can collect it over here. That's distillation. We don't have a good picture of distillation here. They have it in terms of solar energy evaporating water. But, and you can collect it, and you can do that over and over and get a really pure. This is what we do with alcohol, right? Or various distillation processes. And then chromatography. This is special paper, chromatography paper. And what it is, and this is a huge, huge area of chemistry because we have tons of instruments upstairs, fancy, expensive instruments that are based on chromatography. So you can give me a sample of water, and I can inject it into this system. And what it does, it runs through a tube. And that tube is like chromatography paper. It's lined with material. And the substances that are in the water, say I've got gasoline in there, and I want to know different types of hydrocarbons that are in there. They will adhere to the surface of that tube differently, and they'll move through the tube at different rates. Same as with the paper. That's all that's happening there. You have a solvent that's moving up the paper, and you have the paper. The ones that have a high affinity for the solvent and very little affinity for the paper move very quickly, and at the end of the experiment, they're all the way at the top. The ones that really like the paper but don't like the solvent move really slowly, right? And they're down here, and that's how you get this separation. Same thing with a gas chromatograph or liquid chromatograph that we have upstairs. That's how you get separation. Then you hook that up to a detector, and I can say, hey, yeah, you've got lead in your drinking. Well, not lead, because that's not for chromatography, but you've got benzene in your drinking water. States of matter. This is pretty basic. You can just read this. Solids, liquids, gases. Questions? Comments? Extraneous, off the cuff remarks? Anything? Oh, okay. Phase transformations. This is pretty straightforward too. The one that you might not be that familiar with is sublimation. And that is going directly from a solid to a gas, or deposition going directly from a gas to a solid. But I think everybody's familiar with melting and vaporization and condensation and freezing. Your ice cubes in your freezer, if you don't use them much, you go to get them out, right? They're more like little nuggets in your ice cubes. That's because they sublimed in your freezer. These are different ways we can notate molecules. These space filling models, they're more like electron kind of clouds that we'll talk about in the quantum section. It's just a little bit more representative than a bond like this. There's different ways we can write formulas, structural formulas, molecular formulas, condensed structural formulas. Structural formulas are nice because they at least show you the arrangement of atoms. And when you get good, the condensed ones will make sense to you also. Because everybody knows CH3 looks like this. You don't need to write it out, you just write it like this. Ionic compounds. Ionic compounds contain ions, charged particles held together by attraction of opposite charges. Sodium chloride is the classic example. And you see crystals there, and you see schematic of the crystal. So there is no molecules. So water, carbon dioxide, things like this, there are molecules. Those are molecular or covalent compounds. On the right side of the periodic table, non-metals. So we've got if you're on Zoom, I'm pointing to the periodic table. So you've got oxygen, phosphorus, sulfur, nitrogen, all these over here forming our molecular or covalent compounds. Those we have molecules of. But when you put together a metal like sodium on the left side of the periodic table and a non-metal like chlorine, we have a different mechanism by which these come together. And this is ionic attraction. And as a result, there's no such thing, because what happens is this gets surrounded on all sides by chloride ions. 6 sides. So you can have the 4 that are like this, and then 1 in the front and 1 in the back. Okay, and then each of those chlorines get surrounded by 6 sodiums. Why? Because charges aren't stable in nature by themselves. They have to become stabilized. They can't just float around. That's why we don't have ions all over the place, except for in things like plasmas, right? Okay, in water we can, but in water they're going to get stabilized and surrounded by water molecules. Because matter is neutral, and it likes to be neutral. That's stable. Okay? You start pulling away electrons or adding electrons, that creates instability. So each of those chlorines will now get surrounded by sodiums, and as a result, that's how the crystal builds. So I can fracture that crystal ever smaller and smaller and smaller and smaller, and I get a tiny, 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 tiny crystal. You might still have hundreds of thousands of atoms, but you'll never get to a molecule. It's just not stable. The edges of the crystal, of course, right? These guys right here aren't completely surrounded, the ones on the edge. And guess what? Those are the ones that are weakestly held. That'll come off first if you dissolve in water, or react first. Okay? But the majority of the crystal, we're talking about hundreds of thousands and millions of atoms, things like that, the majority of those ions are stabilized by being surrounded by other ions. that make sense? There's two completely different ways in which these compounds form, either ionic or covalent, which are the molecular ones. Those are going to share their electrons. Okay, they're not going to be ions. And we'll get into that, I guess. I don't know if it's 2 or 3. Questions? Those are quiet. Well, the way you're phrasing the question is it's not a molecule because it's not stable enough. It can't form a molecule because it's not stable and they're ions. Okay, so a molecule is not ions. So if I was to take sodium, the element sodium, so I have now a bunch of sodium atoms, and pump in chlorine gas, which is elemental chlorine, a reaction is going to occur where electrons from the sodium are going to be released, and the chlorine is going to pick it up to form the chloride ion. And then they're going to come together and form the crystal. Okay? With hydrogen and oxygen, we simply have shared electrons like this, no charges. These have charges and a positive Cl negative. So what we say is that it's not stable for a single sodium and chloride ion to exist. They're going to attract more and form a crystal. That's what stabilizes it. Does that make sense? Does that help? Okay, well, think about it, read a little bit, and then, reach out if you still have trouble. Other questions? People ask me about different sources. The one I always recommend, of course, is Khan Academy, because it's pretty reliable. There's another one out there some of my students have used, but I always forget the name of it. If you need additional sources and you like videos. All right. So this country's still stuck in the British system, US and British system. The metric system is so far superior, we've just been reluctant to adopt it fully. How many feet in a mile? Too many to remember. Point well taken. 5,280. That's one reason this system is flawed. It's tough to remember. Now, how many meters in a kilometer? 1,000. Everything's base 10. It's easy to remember. Also, not only that, if I asked you how many meters in 3 kilometers, boom, you don't have to do anything. If I asked you how many feet in 3 miles, you got to get out your calculator. Okay? So the base 10 system is far superior. Now, these are the base units, but you can use anything you want. We don't have to use kilogram. These are just the base units. I mean, kilogram's too big for chemistry. So we tend to use more. You can put any mass in any unit you want. Just a kilogram is large, so we typically use milligrams and grams, even micrograms more often. But these are the prefixes with the symbols and all this. And the ones that we use a lot are going to be kilo, centi, milli, micro, nano, and you'll see pico a lot too. Now you might see femto and atto in a question in the back of your book or on smart work, but on my exam I'll focus on I'll keep to these right here. I think on your quiz you had one of the options for your answer was a picometer or something like that. Okay, so there's going to be students that struggle with this, and you have to get past this because. So the one thing I've tried to do with students in the past that has helped some of them, dollar, dime, and a penny. It's the same thing. You guys don't have to think twice. If I go from a dollar to a penny, the number gets bigger. I go from 1 to 100 if I have $1, right? You multiply by 100. It's the same thing. If you go down, the number's got to get bigger. Okay? If you go up, the number gets smaller. Right? As I go down, if I go up, it's got to get smaller. So you're going to be moving, from dollar to penny. I have $1. I moved the decimal place, that's 10 to the 2, right? I moved decimal place 2 places, 1, 2. I went up with 100. That's all this is. It's telling you how many places to move. Okay? People make this more difficult than it is, partly because our brains don't work well with negative exponents. It's a little tricky. Now, if you're going from micro to nano, 1 is 10 to the minus 6, 1 is 10 to the minus 9, so it's a difference of 3, which is 1,000, 10 to the third. You would change it by 3 places. Whether you're moving up or down, it'll get larger or bigger. That's all you got to do is kind of like look at the difference between these. If you don't want to go, like if you're asked to convert from this to this, instead of going from this to meters and from meters back to micro, you just use the difference between these two to move it 3 places. That's all. Okay? So you got to get comfortable with that. So, questions. We'll do some of this when we do some of the practice stuff. Temperature scales. So these are a couple of formulas that were on your outline, right? So these are ones you need to know. They were on the outline, correct? Okay. Now, some people give a formula for Fahrenheit over here already solved out, but you guys should be able to do the algebra. So if you were given Celsius and you had to solve for Fahrenheit, you got to be able to solve that. Some people solve it for you already, but that's just another equation to remember. You guys should be good enough in algebra to solve that for that. You wind up with, you bring the 32 over, you get, you wind up with degree. Wind up with 9/5 degrees C plus 32. If you bring the 32 over, and then you multiply by the reciprocal, you get 9/5. Oh, so I'm sorry, I got the parentheses there. Oh, that's in the parentheses. Sorry, I did that right. I'm okay. This is inside parentheses here. So we do the, you do the reciprocal multiplication first. Bring that over, then you add the 32. So we can convert between any of these. And most of the time on an exam, you could probably just use 273 because, it's multiple choice. So we're not worried about the 0.15. So let's do one of these. The temperature of coffee from the student union is found to be 205.43 degrees Fahrenheit. What is the temperature on the Celsius and Kelvin scales? So you can take a minute and just start working this. I don't have it solved, so I don't know what the answer is. It's good to have your calculator in class also. Take a minute and work it out and see what we get. Work things out in class. Make mistakes, you figure stuff out, and you do it. Make a mistake now, so we'll put it on the tape. So it's always good to do. Raise your hand if you get one of the answers or want to share it. What'd you get? 96.35 Celsius. Okay, anybody confirm that yet? You got that too? We're good. So we need a Kelvin temperature also. That's easy enough to say at 273.15. What'd you get? 369.1. 0.75. 751. Oops. And is that right? We do not use a degree symbol for Kelvin. There is no degree symbol, so just K. Does anybody need me to explain how we got these or show this? Yes? Okay, so we've got this one right here. They're going to use this formula right here. So we're going to take 5 nines temperature Fahrenheit. I don't have a calculator here, so we need 205.43 minus 32. Whoops. Do you have a calculator here? So what's that right there? We need that number. What is it? Are you kidding me? Is that what you got? Okay. And then we're doing this. So we've got basically doing 5 ninths the temperature in Fahrenheit minus 32, right? So we now have 5 ninths times the 173.43. That's what you calculated after subtracting 32. So now you have to take 173.43, multiply it by 5, and divide by 9. And that should give us our temperature in Celsius. And you should get the 96.35, okay? Now all you have to do is take that's Celsius, and add 273.15 to get your Kelvin temperature here, because that's the formula. Kelvin is Celsius plus 273.15. Thank you for asking that, because I'm sure there's more than just you that needed that. Question? You good? All right. What's next on tap? So there's always uncertainty in measurements. Okay, you can use the same scale and put the exact same mass on it. And if it's a pretty precise scale that gives you a lot of digits, you can get different numbers. Okay, oils from your finger can add mass. Air blowing in the room can affect the scale. That's why sometimes we put these plexiglass plates. I have a high precision scale in my research lab, it's surrounded by that. Okay, so here's these measurements. And they're all pretty close. They're all 2.527, but that last number's vary. Okay, so there's always this uncertainty. And significant figures, I always feel like chemists spend a little bit too much time on it and emphasize it too much. Physicists don't preoccupy themselves with significant figures quite as much. It's important in the lab, and it's important when you're doing calculations from data. And it's important that you understand that what the calculator spits back at you doesn't deserve to make it onto a piece of paper just because it gives you 13 digits. Okay, that's the key to it. So I will ask questions on it on quizzes and exams, but I'm not as bad as some faculty in terms of how I emphasize it. So So these numbers right here are pretty darn precise. And that is, they're all very close to each other, right? As opposed to if we had a number like 2.617 or something. That wouldn't be very precise with that group there. Okay, they're all 2.527. It's only that last number that's changed. These are all pretty precise. Now, some numbers we have are exact. And what we mean by that is there's 2 dogs. That's an exact number, or 2 pennies. You can't have 2.5 dogs. I mean, maybe one of them is pregnant, I don't know. But still not a half. Still 2 dogs. Those are exact numbers, numbers of steps. Okay, numbers of objects. But measurements are not exact because there's error associated with them. These aren't exact. You can see that. They're different every time you measure. Some conversions are exact because they are exact. And that is 1 inch is exactly 2.54 centimeters. That's an exact conversion. That means it's 2.54, 0, out to infinity number of zeros. That's what it means. Okay, it's not just rounded off. Those are all zeros after it. That's what exact means. So I'm getting to significant figures here, what it actually means and why we use it. So here's precision. The best way it's ever described to me I've ever heard it is on like a dartboard. If they're all really close together, then they're precise. So these are precise, right? Because they're all grouped together, and these are precise because they're all pretty grouped together too, right? But only one of these is accurate if we assume that the bullseye is the true value. So for instance, I'll get a standard from EPA for like a lead concentration. And I'll have my students run through a method and then measure that lead, okay? And they have to see how close they come up to what is actually supposed to be in there based on what EPA says. That's how accurate it is. So we have to know that our method is sound. So if we can go through this method with this lead standard, and then we can analyze and get the number that EPA says is in that bottle, then we know we're good. And now we can start measuring samples in water or whatever and know that our data and our method is good. So if this is the true value, right, then these are accurate and they're precise, but these are not accurate down here, right? They're not accurate. And this, well, you're just terrible in the lab and you better go find another career because you're not accurate or precise. Usually when you have something like that, when you have something like this, it usually means that there's like something off in the lab, like your scale wasn't calibrated because everything's off and they're all off the same and they're all grouped together. When you get data like this, well, you got problems. And figuring out what went wrong. Questions about the difference between precision and accuracy? Yes.
On the quiz, there was a question and it was asking how precise it was. And it was like the first decimals were all the same, but all the rest of them were different. So would that count as precise? Because they had a similar number, but then
It really depends on how many decimals. I can't remember the question, to be honest with you. It depends on how many decimal places there are and how much that variation is. I'll have to look at it. And then once I release the quiz, you'll be able to look at it too. And if you have a question and I can look at it, we can communicate again. But yeah, so it's a good question because at what point is it not precise? And we try to make it at least, so sometimes you get data like this. Okay. And that's when you can actually do a statistical test and say, you know, that's an outlier. We don't even have to consider that one. Something went wrong. We can throw it out. But that's a good question because there isn't any real definitive thing that says, okay, at this point it's precise, at this point it's not. You just kind of have to go with each case by case scenario. But I'll look at that one specifically too. Now that you brought that up. Other questions? And I can't remember if it was a precision and accuracy question, like you were saying, if these are, yeah, okay. And I don't remember if it was pooled or not, so there might have been multiple questions too. All right, so significance is based upon our confidence in a measured value. Different instruments can be used to determine a measurement with greater degree of certainty. I have both of these types of scales in my lab. The one at the bottom gives me more precise numbers, gives me more digits, right? That's always better. Now, the last number in a measurement is always the one with uncertainty, right? Because depending on what the scale does, now imagine these two scales, right? Let's say this one gives me, I can't even read that down there, it's so small. 1, 2. So let's say we get a measurement of mass of 2.5671. Okay. This one would read it as 2.57, right? It would round it off. So you never know that last number, what it actually was or is based on how the scale rounds it off. So the last number is always uncertain, but it's still considered one of the significant digits. So these are all significant, and these are all significant. It's just realizing that last one's the one with uncertainty. And the reason we do this, you know, I just read an article the other day, just a blurb, it was an abstract, it wasn't an article, but they just calculated pi now out to a ridiculous number of digits. It's something like in the billions. It's ridiculous. You know, so now they know what pi is exactly out to so many digits. Up, it was something like a billion. When a number is super precise, that's important. Like if I'm reporting, say the amount of lead in water, and I tell you, let's say the EPA, I forget what lead is. I think it's 15 parts per billion is the EPA allowance. It's got to be below that. Don't quote me on that, but anyway. And I tell you, I've got, you know, 10 parts per billion, right? But I report it like that, which actually means one significant figure. And for all I know, that could be 10 plus or minus 15, plus or minus 2, plus or minus 1. There's no way of knowing. So by giving a precise number, by recording it with a lot of digits, you're telling someone this is the level of accuracy or precision, I should say. It's not accuracy because there's no true value. Well, there is a true value. We don't know what it is. If you just take a water sample and measure it, no way of knowing what the exact true value is, right? You can only do is measure it. So if you know it really precisely, and I know it's 10.0000, I want to report that because that lets those people sleep at night. They know their water's below the EPA lead level. But if you just report it like this, they're like, well, heck, how accurate is that? How precise is that number? There's one significant figure. So all non-zero numbers are significant. The zeros at the beginning of value are never significant. Why? Why are zeros at the beginning of value never significant?
It sets the decimal.
It's what?
It sets the decimal.
Right. It's just a placeholder, right? Setting the decimal. Because I can convert, someone else said it out there too. I could say this, I've got 1.0 milligrams, right? Now that's zero significant. We're getting to that down here. Now I want to change that to grams. How many grams is that? Which direction are you going to go? Is the number getting smaller or bigger? smaller, right? And 3 places, right? 1,000 is milli. Right? That's how many grams that is. Now, I shouldn't all of a sudden have gained 3 significant figures just because I put it in a different unit, right? The number doesn't get more precise just because you change the unit. So that's why those can never be significant. Now, zeros after a decimal point are always significant. That's what I was saying over here with the lead. If I know it out to that precision, it's exactly 10 out to 1, 2, 3, 4, 5, 6, 7 digits. That's what I'm telling you. The only one that's uncertain is that one, but it's still a significant figure. But you know that is 10.000, and then it might be, 01, 02, 03, 04. We don't know what the next number is. We know it's not 05 because it would have rounded up to 10.0001. So you really don't know. So those leading zeros cannot be significant. Zeros at the end of the value, no decimal point, may or may not be significant. That's why we like to put things in scientific notation to clarify that. So instead of saying 96,500, we'd say if those 2 zeros are insignificant, then we pay 9.65 times 10 to the 4th. If they were significant, we'd say 9.6500 times 10 to the 4th. You don't want to drop significant digits. You keep them. But by putting it in scientific notation, it eliminates that uncertainty of whether or not the number was significant or not. Zeros between numbers are always significant, obviously. Questions? So we just learned those rules. That's the easy part. The hard part is in calculations. And this is the part that I don't stress a ton. I'll probably give you like 1 or 2 on the exam, and there'll be simpler ones. I'm not going to give you advanced ones. I might have assigned you some in Smart Work or the back of the book just to get you tuned up, But the exam ones will be pretty basic. Because like I said, I don't stress this too much. It just comes with time. You get better at it. It's not a deal breaker if you add 1 extra digit, in the lab or something, you're doing one of your lab. They might take you off points depending on how they're grading significant. Well, when my students come to do research with me, I tell them right away, I say, okay, this is somewhat important. How many digits you report to me? How many, and when we put our numbers on a poster or on a paper, did we really have that precision? If not, you shouldn't be reporting that. So the number, what time are we at? Okay. What do we got? Well, we're doing pretty good. I guess we'll have to finish. We're almost done, actually. But we can finish this up. We got time on Tuesday. Because it won't take me 85 minutes to do a whole review. All right, so got to be determined by the experimenter based on the numbers. And what we use is this. Where is it? I thought I had it here. It's maybe on this side. There it is. Weakest link principle. Only apply the rules at the end of a calculation, not in the middle. And that is this. This is why. If you do a calculation, right? And let's say I've got something like okay, and I get a number here. And the number should have 2 significant figures because the weakest link principle tells us can't be greater than the one with the least number of significant figures. Okay, that's what this says. That's for multiplication and division. Number of sig figs in the result is equal to the number in the least precise measurement used in the calculation, right? So 6.8 times 2, the answer should be 13 2 sig figs. Why? because this one only has two sig figs. Does that make sense? Don't worry about the division and that's multiplication. Don't worry about addition and subtraction yet. Now, going back to my example here, this answer is going to have two sig figs. If I'm going to use this number in another calculation, you don't want to take just two sig figs. You want to take the whole thing that your calculator gives you. And then say I got to multiply it by 3.0. So do not take two sig figs and multiply it by 3.0. Take the entire number, multiply it by the 3.0, and then report your number to two sig figs. Okay? Because it's like a rounding error. You got to be careful. If you do that multiple times, you can seriously affect your answer. And we'll actually see that when we do like empirical formulas, that if you do rounding throughout the calculation, you'll come up with the wrong answer. I've seen it happen numerous times. So when we do empirical formulas in chapter, whatever that is, you've got to do a series of steps of calculations, and you got to make sure that you don't round off things too early. So don't worry about sig figs to the very end. Questions? So with addition and subtraction, it's a little bit different. The number of sig figs in the result depends on the number with the fewest number of decimal places. Because if you add these up, think of it like this: 11.934 plus 6.8. Oh, there's only two numbers. Okay. You truncate it here. If you were to report that to two significant figures, you'd have to report 19, right? And that doesn't make sense because of decimals, it's a little bit different. So that one you would report is 18.7. So it's still a weakest link principle. It's just the rule is slightly different. So just truncate it like that and say, okay, one decimal place my answer is going to have. And you could come up with examples where you convince yourself, like if you had numbers like this, 0.009, something like that, you're going to lose that whole value there when you add that and carry that number of that decimal place. No, that's not the right example. No, that's the same because you still have one. I forget. There's a couple examples you could do where it's really obvious that if you use the rule for multiplication and division, you'll like misreport the number a ton. I think it's if you. I know what it is. You have a link. Anyway, I can't think of it. All right. Unit conversions. This is an exact conversion. I mentioned that already. This is just dimensional analysis. So what we're doing here is simply just like numbers. If I multiply 1/5 times 5, these cancel out, right? Same with units. That's all dimensional analysis is. Putting your kilograms down here so you convert to liters. This is your conversion. Desired units over initial units. This is dimensional analysis. And using this to get to the correct answer, to lead you through to the correct units, is just wonderful in terms of once you get familiar with it and you get comfortable with it. It just corrects, it keeps you from making a lot of mistakes, basically. And we'll do a bunch of this on Tuesday. So this is what we'll finish with. This problem right here. A pediatrician prescribes the antibiotic amoxicillin to treat a 2-year-old child suffering from an ear infection. The therapeutic dose is 75 milligrams of the drug per kilogram of body mass of the patient per day. The drug is administered twice each day in the form of a flavored liquid that contains 125 milligrams of the amoxicillin per milliliter. If the child weighs 28 pounds, how many milliliters of the liquid should be administered in each dose? This is what I mean by word problems. This seems like a mouthful, and it is, but the math is not difficult. It's just a couple conversions, dimensional analysis. True story, we actually had this situation with my daughter when she was real young, and my wife, being a fashion design major, handed me the bottle and said, okay, you figure out how much to give her. Because it really was this same exact thing. Just like this, it was like milligrams per liquid, and it was like, okay, so we weighed her and we converted her weight to kilograms, right? Because, you know, I would give you that conversion, did they not hear? 2.2 pounds per kilogram. You can just use 2.2. So we weighed her on the scale. We converted her weight to kilograms. And then once I knew her weight in kilograms, of course, well, we had to give her 75 milligrams per kilogram. So I can just multiply, right, the 75 milligrams per her kilogram body mass. Okay. And then I know how many milligrams she needs. And then I know the drug contains 125 milligrams per milliliter. So if I divide by that, I can figure out how many milliliters she gets, and then divide it by 2 because she gets 2 doses a day, right? So those are the ones we're using. 2.2 milligrams, 75 milligrams per day. A mil contains 125 milligrams and 2 doses per day. Dimensional analysis. Start with the child's weight. Convert it to kilograms. Figure out how many milligrams they need, right? Just follow the units across. And you see this. And look at what we see. Convert pounds to kilograms. Get rid of the pounds. 75 milligrams per day. Okay. 75 milligrams per kilogram per day. So kilograms are gone. At this point right here, this is how many milligrams per day the child needs, because that's what the units tell you. But it's a liquid, and each mil contains 125 milligrams. So put the milligrams in the denominator so you can get rid of it. Now you know how many milliliters the child needs, right? And since there's 2 doses per day, we get rid of the days, and we get 3.8 milliliters per dose. Dimensional analysis. You read that, it's like, it'd be a little overwhelming. Then you say, okay, well, got the weight of the child, let's convert to kilograms. I know how many milligrams per kilogram the medicine is prescribed. I can figure out the milligrams. That's what I did here. These 2 steps. Then it's a liquid, and I said, okay, well, there's 125 milligrams in each mil. Right there, right? So that's the next step. And then she's supposed to get 2 doses per day. Divide by 2, you have your answer. Problem like this on the exam, there'll just be one of these types, because it takes a little bit of time to solve, even though it's not super mathematically difficult. It's just calculation. It's the word problem that's difficult. I'm not underplaying that this is a tough problem. I'm just saying the math is easy. It's just multiplication. It's setting it up and understanding, and that's where the dimensional analysis helps. Questions? Oh, thank you. Thank you. So we reported we round the result to 2 significant figures because the child's weight and the therapeutic daily dose both have 2 sig figs. Very good question. The number of doses per day, 2, is exact. So that's not one significant figure. That's an exact number. right? You give exactly 2 doses. So that's an exact number. Excellent question. And then we report it as 3.8 because we want 2 sig figs. All right, look for the quiz to release. There's the summary of the